All right, so let's leave Mars and move farther out in the solar system. So the Dawn mission has been orbiting the dwarf planet Ceres, or the largest asteroid Ceres, depending on what you would like to call it. And that's been there for about the last, it's coming up on 3 years now. And one of the things that got people's attention very early on was this, these bright spots in this large crater. This is about a 60-kilometer diameter crater. It's called Occator. And these splotches end up being the brightest area on the entire moon, or on the entire asteroid. And so they've been spending a lot of time trying to figure out how were these formed and what is it made of. And so last summer, they took measurements with a visible and near-infrared spectrometer. And so what we're looking at is this area. So here's the large bright spot, and then the smaller ones are off here. And the color coding here is they're looking at the spectrum of carbonate salts. And so red means that's a high abundance, yellow, a little less, blue, less than that, and then you get out into the gray and there is none. And so they determined that these are salt deposits, not ice or something like that was also proposed. But the thinking is that these were caused by a hydrothermal environment where there were either geysers or hot springs going off that would carry the dissolved salts to the surface, and then the water evaporates because there is no atmosphere, and what's left behind is whatever was dissolved in the water. And so that was an interesting result. But there's some new thinking on this now, where they've done a lot of examination up close of these areas, looked in multiple spectral bands, and the model now is that this was caused by the impact that created the crater itself. And it made a sort of a hot spot in the center of the crater that almost certainly had molten rock in it. And under the assumption that yes, there was water embedded in these rocks, you likely had a subsurface lake, and the various dissolved gases in that pressurized the system and forced the water to the surface. And by applying this model, they believe that these deposits are actually younger than the crater by about 30 million years or so. And so they are placing an age of about 4 million years for when these were created. And in geologic speak, 4 million years is yesterday. So these are very recent features. And so what Dawn has been doing over the course of most of its mission, it first put itself into what was called a high altitude mapping orbit. That was about 15,000 kilometers or so above the surface. And then every 3 or 4 months, they'd cut that in half, or roughly in half. And they ultimately ended up in an orbit that was a little less than 900 kilometers from the surface. And they essentially mapped the surface from each of these orbits. And what they're doing now is using their ion propulsion to raise the orbit again. They're pumping it up to about 50,000 kilometers. And they want to do studies where the sun is directly behind the shoulder of the spacecraft, if you will. So it's called looking for the opposition surge, which is when you have direct sunlight coming down on the surface, and it's not off at an angle. And that does a number of things for you. It removes all of the shadows in the area directly underneath the spacecraft, and it allows you to come up with very accurate models for what the reflectance of the surface is. You're not having to worry about what fraction of the surface has rocks sitting on it with shadows being cast off to the side, for example. And so that's their goal for the next multiple months, is to do that study from the high orbit. And that will take them through late this year. So I'll update you on that when we have some new data. We should have some of these opposition surge images coming in within the next month or so, and they should look very different than what we've been seeing